It all started about 10 years ago, I think, or so, maybe more. It was around the time when vehicles on the road, cars, the same cars you and I drive, when they started to transition between or from the old incandescent red brake lights to the more modern LED brake lights, right? I was a car guy big time back then. All the newest and latest cars coming out. I used to love, paying attention to all that. To a certain extent, I still do, but not as much. But still, when they started transitioning to these LED lights, oh, I was a kid in the candy store, right? Because as I explained in one of my previous videos, I've always been fascinated with lighting and with LED lighting. And so suddenly I start seeing this form of lighting on vehicles, the other thing that I really like. So I was like, wow, this is great. I have to admit though, the excitement was fairly short-lived. So if I was driving and the vehicle was in front of me with these modern lights, I would sit and stare and be like, oh, they're so beautiful, so vivid, so rich. I would love the look of the LED light coming off of these brake lights. And then at nighttime, let's say it actually happened more at night, even during the day, but if a vehicle was driving beside me and it was moving, relative to my vision and the brake lights came on momentarily, I noticed that it wasn't a solid stream of light. I noticed like it was like a trail of flashing lights. Right. I was like, what is that? That was weird. Maybe, and then I dismissed it. I thought maybe it was just, whatever. It was just an artifact of the environment that I was in. But then I started noticing it more and more. As more vehicles started getting these LED lights, I started noticing that I see a bit of flashing. It's like the light would be on, then off, then on, then off, then on, then off. But I couldn't quite, it was strange because it's not like it was flashing in front of me. It wasn't visibly flashing, but I could almost sense or perceive that flashing. And it was more obvious if the light was in motion relative to where I was looking. So I would see like this trail of flashing lights. Anyways, I thought that was a bit weird. So I started doing some research into it, and then I discovered what was happening, right? There's the way that that light was maintaining its intensity was this technique that I'm going to get into. um, but I started seeing it, more than just on the road because that was, like I said, one of the first places I saw it. But then I started seeing it in interior lighting. I think it was a hotel room I was in at once. And I was thinking about the lights, thinking, man, I'm starting to get a headache in this room. And I couldn't quite understand why. And then I started noticing as I moved stuff in front of me, it wasn't whatever I was looking at wasn't a smooth motion. It was similar to seeing those trails I saw on the road. And then I did an experiment. I just started moving my hand really fast in front of my eyes, and I noticed that my fingers would, they would appear and reappear in different locations. Again, this is happening really fast, so it's barely noticeable, but it's there. I started doing some research into this phenomenon, and I discovered that most people out there don't see this. Even, when I asked people, I said, do you notice that? Most people are like, ah, you're crazy. I don't know what you're talking about. You're just seeing things. But then I also discovered there are people out there who do notice it. And apparently I'm one of them. I'm one of these people, a small percentage of the population, it's sensitive to flicker, or we can see things happening faster than I guess most people. So the rate of I don't know what you call it, the rate of the frequency rate that we can see with our eyes or perceive, I should say, tends to be a little bit higher than what the majority of the population can see. And so as a result, I see this flickering of the light, whether it was in the car brake lights or in the hotel. What if it's at home? I mean, for me, I would just get a headache sitting in a room with this kind of lighting. And so I'm on a mission now to eliminate the world of this terrible lighting. And the methodology used, it's called, well, it's more commonly known as its abbreviation, PWM, or pulse width modulation. It's a technique used to control the intensity of LEDs so that it appears to be consistent. And it's also used to dim it. I can't stand it. We've got to get rid of it. Anyways, when I did the research, I thought, why are people doing this? And at first, it seemed to me that there seemed to be a sensible reason behind it. So the LEDs that they're using this PWM methodology on, they have a rating, a current rating. As you saw in one of my previous videos, that small LED that I used had a 20 milliamp rating, or current rating through it. And so if you're running your LED at that level or at that current, then it's operating at peak efficiency. Now I said you can go a little bit higher, but not for very long. You can certainly go a little bit lower. But if you go higher for too long, it's going to burn out the LED. Well, it turns out you can actually run almost any LED at a much higher current for shorter periods of time. Look, I mean, take a look at this. So this is one of the data sheets. I'll bring this up on the screen. There we go. So this, I just found this online. This isn't actually the same LED that I showed in one of my previous videos. I don't actually have the data sheet for that one. So I just searched online. I found this. It looks a lot like it, but it'll suffice for our purposes. But if I scroll down here in this data sheet, I'm going to find the place, there it is, where it actually says the continuous forward current. So this is the rating of this LED, and this one's rated for 30 milliamps. So the highest consistent safe current that you can push through this is 30 milliamps. It says, look, the second line here says peak forward current, and it says a whole bunch of gibberish here with duty. I'll get to that in a minute, but it says 100 milliamps. So wait a minute, this says that I can triple the current, more than triple the current going through this LED if I follow these rules over here of maintaining a duty whatever, /10 at 1 kilohertz. That means I can run this at higher. I looked at another data sheet for another LED. This is, again, not the same one that I have. It actually looks a lot like it, but it's not exactly the same. Or maybe it is, maybe it isn't. I don't know. But if I scroll down to the specifications here, you'll see that this also has a DC forward current of 350 milliamps, just like the one that we saw in one of my previous videos. I was running, or it was capable of running at a higher current. But it also says just below this, a pulsed forward current, similar, technical jargon here, at 700 milliamps. I could double the rating of this LED or double the current that goes through this LED if I pulse the forward current according to these specifications. So, I mean, all of this means is that if I follow these specifications, I can then pulse the current going through the LED for a number of different reasons. One of those reasons is to dim the LED. So if you pulse it, and we'll get to this in a little bit, if you pulse it so that it's on, for a certain percentage of time and off for a certain percentage of the time, it's going to perceive to be dimmer. Our eyes are just going to blend it in and we're not going to really notice that pulsing. The other reason, though, that they're pulsing this, and this is what I discovered, which is kind of surprised me at first, is that they're deliberately pushing these LEDs into a much higher current, just like you saw on the data sheets. But they're doing so in order to give a brighter perceived illumination. So our eyes see it as actually being brighter. And we do see it as being brighter. The downside, though, is that it's flickering. And while most of us can't really notice the flicker, some of us do. And I got to tell you, we suffer, right? Because it bothers me. And if it bothers me, it bothers others out there. So yeah, I'm on a mission to get rid of this dimming mechanism or LED driving mechanism of PWM or pulse width modulation. It drives me insane. So I mean, how are they capable of doing this? The LEDs are capable of doing this because they're designed, they're very precise electronic components, right? LEDs are kind of like scalpels if incandescent lights are chainsaws, right? So the old incandescent lights, they make a lot of heat and they waste a lot of energy, it's like chainsaws. They're noisy and do all sorts of stuff. Whereas a scalpel is designed to cut, and all the other stuff, heat, all the other wastage, it doesn't do all that much, right? It's very efficient at its job, much like an LED. It's designed to give off light at a very particular wavelength. And so because of its precision, these LEDs are able to turn off and turn on rather quickly, much faster than you and I can perceive it, on the order of microseconds. And so manufacturers are leveraging this capability or this ability of LEDs to be able to pulse the current through it so that even though you're not actually generating more light, we perceive it to be brighter than it actually is. And it works. So, I mean, that's how it actually works. But in the last video, I mentioned that I wanted to show you a circuit that leverages this kind of capability. And quite frankly, it's actually not a different circuit. It's just a little bit added to an existing circuit. So let's look at the existing circuit here. I'm going to bring this up on the screen. So if you remember, this was the last circuit that we left off with, right? This was a circuit that was giving us the ability to drive our LEDs much more efficiently. And so in order to utilize PWM or pulse width modulation, we just have to adjust this a little bit. In fact, if you go back to the original website where I got this or got a variation from this design from, if you scroll down a little bit, you'll see that the author of that original website had actually indicated that you can add PWM dimming to this design relatively easily. All we had to do was basically put another lead in here and feed in our PWM signal. If you feed it in to this point right here, then what's going to happen is this Q2 or this MOSFET is going to turn on and off rapidly. And as a result, the current through this LED is also going to turn on and off rapidly, resulting in this pulse width modulation business, which is going to allow us to dim it. So it's not necessarily a new circuit, it's just a new methodology. And you can add a PWM, I guess, input to almost any circuit design, even the more simple one that you saw us do right in the beginning. You can pulse the current going through there and you can achieve the exact same result. So, I mean, you can do that, and arguably it looks pretty easy to be able to push this circuit in. The alternative to adjusting the intensity, we talked a little bit about this, is adjusting this parachute resistor, right? If we adjust this parachute resistor, then this would also adjust the current going through here. But I mean, you can imagine, right? Changing this resistor on the fly or putting in some electronics to allow this resistor to change is probably going to be more complicated. It's going to be a little bit more complex. We're going to get into that in the next video, actually, just doing some of this electronic circuitry to make this resistor variable. But it's going to be more complex. It turns out it's far easier to plug in a PWM signal here, leave this thing fixed, and have this pulse width modulation signal adjust the dimming. So, I mean, from an easeability standpoint, it's a lot easier. It's a lot easier to be able to use this methodology to dim your LED or maintain a consistent brightness of that LED rather than putting in some complex hardware. So, I mean, I guess that's one of the reasons they do it. Let me talk about some of the details about what this thing is. So let's zoom in, or not zoom in, but let me show you another chart, what this PWM actually is. So this is a representation of that signal. Perhaps this could be that PWM signal going into the last circuit. So let's look at this. I mean, I've drawn this on graph paper, and let's assume that each and every one of these little squares, right, in terms of time, so we have time going this way, is 1 millisecond. Millisecond's a thousandth of a second. So each square is 1 millisecond. Well, that means that each cycle of this wave is 10 squares. So that would be 10 milliseconds from end to end. All right. Now the low level of this signal means that this LED is off. And the high level of the signal means the LED is on. So what I'm drawing here is I'm drawing a wave pattern that rapidly turns this current through the LED from off to on to off, well, so off to on to off to on to off to on. And it's doing this every 10 milliseconds. So if you do the equation for the frequency is 1 over 10 milliseconds, which is 100 hertz. So what this means is this on and off cycle, based on the numbers you see on my page here, is that this on and off is happening at 100 hertz. And if I look closer at this, the signal is off for 5 milliseconds and on for 5 milliseconds. Right? That results in a LED that's on 50% of the time. This is that pulse width modulation of 50%. We call it a duty cycle. But if this is 50%, that means that 50% of the time the LED is off, 50% of the time it's on. And if this thing is happening 100 times a second, then that's happening much too fast for our eyes to actually see. But I'll tell you, at that frequency, I can very likely perceive it. And you may be able to as well. Some of us can definitely perceive this flicker at 100 hertz, especially if you or the light source is moving. Anyways, so that's basically what you do in order to get a 50% on and off rate for that signal. Now, if we're going to change this signal, I'm going to change this. I'm going to draw a new signal in here. Let me draw this new signal. So let's Let's bear with me while I draw it, and I'll put some numbers in to show you what's going on here. Here we go. All right, so what I drew here is another variation of the same signal. This cycle is still happening every 10 milliseconds. So my frequency is still 100 hertz. That hasn't changed. But if you notice, the LED is off for 3 milliseconds and on for 7 milliseconds. That means the LED is going to be on for 70% of the time. As you might imagine, this is going to give us a much brighter LED, even though we haven't actually changed the current level, nor have we changed the frequency. We've just changed the duty cycle, and we can have this thing on for 70% of the time. It's going to be brighter. Let's look at the other possibility. All right, so here's another example where it's the same frequency. This cycle happens every 10 milliseconds, so I'm still at 100 hertz. But notice now that the LED is off for 8 milliseconds and on for 2. Well, that's going to give us an LED at about 20% of brightness. So using, or I should say, varying how much or how long that signal is on is going to give us a different intensity of our LED. So this is exactly what that PWM is. It's pulse width modulation. We're modulating the width of this pulse, even though we don't change the frequency. And by doing this, we can actually achieve a different intensity of that LED. And that's basically what happens is with these signals, is if I go back to this, that PWM source, we're actually feeding in that signal that you just saw me create. How do we feed it in? Well, we'll get to that in a second. But let's take a quick look at this. I want to bring that one of those data sheets back because there was something really interesting there. If I bring that old data sheet back, let me bring it up on the screen here. There we go. Okay, so this is the same data sheet where we're looking at earlier, where we actually had that DC forward current of 350 milliamps and then a pulsed forward current of 700 milliamps. Take a closer look into these numbers here. So this is telling me that, or this is telling us that the time for the pulse, or the time for the upper pulse, must be less than 100 microseconds. So that means that this LED has to be on for less than 100 microseconds. You can do 100, but it's got to be that or less. And then it also said the duty cycle needs to be 0.005. So that equates to, well, the drawings and the mechanics, the drawings you saw me do earlier, that equates to a 5% duty cycle. Or actually, no, my mistake, 0.5% duty cycle. So if I do the numbers on this, let's bring the other sheet back here. So let's pull this over here, and I'll bring the other sheet back. Okay, here we go. We're back here. If I were to draw the pulse according to the specifications that we just saw, it would look something like this. That's what it would look like. The data sheet is telling me that I've got to maintain a duty cycle of 0.5%. So if I were to maintain a duty cycle of 0.5% at this same frequency, oops, all right, the math tells us that that little peak of when this thing needs to be on is 0.05 milliseconds. So that works out to about 50 microseconds, which is less than what the specifications on the sheet tell us. So we're safe there. But if I keep this frequency at this rate, this LED is basically off for 99.5% of the time, and for 0.5% of the time, it's on. It's basically doing a tiny little high-intensity flash every 9.95 milliseconds, or every 10 milliseconds. It's going to flash like that. Now, I don't know about you, but at 100 hertz, if I had a room full of LEDs doing this, I would almost guarantee you that I would feel it. And it would almost certainly, give me a terrible headache. But that's how the pulse width modulation works, and it's actually quite simple to do that. I mean, in order to make this happen in our circuits, all we really have to do is we have to add a microcontroller into the mix, and out of that microcontroller comes that signal. Now, microcontrollers are really easy and cheap and widely available, which means that comparing this solution to the complex resistor solution, well, this is often easier. And fundamentally, that's why it's done. And this is part of the problem. It's so easy to use PWM to control our LEDs and our lighting that that's why it's done. Electronically, it's simpler and cheaper to implement. You don't have to buy a lot of parts. You can actually adjust those pulses using software. So you can write software to adjust those pulses. And if later on down the road you wanted to change it, well, you just update the software, you update the firmware, and you have a new upgraded light. So in terms of longevity and in terms of ease of use, the software solution makes a lot of sense. I mean, it does. There's some points to be said about that. But of course, the downside here is that you have to deal with this flicker. So, I mean, it's easy. It's widely available. That's why it's done. And honestly, if you make something easy and widely available and cheap and easy to do, people are going to do it. Right? So again, I will reiterate my point. We've got to stop using pulse width modulation for illumination practices. PWM is successful for a reason. It's really, really effective at certain things. As you can see, we can certainly use it to exceed the normal static limits of these LEDs. And as you've heard, I personally am one of those people who don't like it. But it has a lot of great applications. So I'm not saying PWM is bad. What I'm saying is stick to the applications which it's good at. Pulse width modulation is phenomenal at motor control or controlling the speeds of spinning motors. It's beautiful. If you look at the electronics designed to do that, it's easy. You can control it using software, and it has no ill effects. So motor control is fantastic. Controlling the heat on electric stovetops, PWM is used to do that as well. Phenomenal. It really effective methodology for controlling the level of energy going through an electric stovetop. And there's lots of other places where it should be used, or it can be used effectively. But let's keep it out of our illumination because some of us don't like it. I don't know. I'm going to remain on this rant forever. But I think for now, it's probably enough on the video. I hope you enjoyed my rant. Oh goodness. So you haven't subscribed to the video yet, please do. I won't be ranting. I promise I won't rant too much on my next video. In fact, what I'd like to do on the next video is I want to start to adjust the circuit that we've already designed and implement some dimming methodologies using non-PWM methods. So I'm going to do some of the more complex hardware I guess like a hardware implementation of doing some dimming on that. But it's going to be fun. We're going to figure out how to do it, and we're going to try to be a little bit creative here. But again, we're going to leave this pulse width modulation out of our lighting circuit. Until then,